the first video in this series, we looked at what electricity is and the principles of electricity that allow current to flow through a circuit and do work. In this video, we'll look at the subject of wiring diagrams, the road maps for the electrical circuits in an automobile. Then we'll look at the different types of circuits you're likely to find on a passenger vehicle. And we'll look at the use of a digital multimeter and how it is used to measure voltage, current, and resistance. After viewing this video, you should be able to identify the common electrical symbols used in a wiring diagram, identify the elements in a circuit, describe the characteristics of a series, parallel, and a series parallel circuit, understand the use of a digital multimeter in electrical circuit measurements and diagnosis, and describe the different types of circuit faults and their effects on electrical circuits. Wiring diagrams are the road maps for the electrical systems on a passenger vehicle. They show the route of the power flow from the source through the switches and loads to the ground. Just as you learn to read traffic signs as you learn to drive, understanding the symbols in a wiring diagram will help you trace the route of power through the circuits. Power flow starts at the battery. The symbol for a battery is 6 heavy lines, each separated by 6 small lines. Each of the heavy lines in the icon represents one cell of a 6-cell 12-volt battery. A fuse or fusible link is used to protect a circuit against a high current flow that could damage the circuit. A fuse is represented by a wavy line between two circles, while a fusible link includes the symbol for a fuse inside a rectangular box. Circuit breakers can be used instead of fuses. A circuit breaker is shown as a smile-shaped black line over 2 black dots. Diodes are often used as one-way streets. Diodes allow the flow of current in one direction only and will not allow the flow of current in the opposite direction. The symbol for a diode is a dark triangle pointed to a perpendicular line. The direction of the triangle point is the direction of current flow through the diode. A light-emitting diode is a diode that acts as a lamp, illuminating when current is flowing through the diode. The symbol for a light-emitting diode is the same symbol as a diode enclosed in a circle. A resistor is often used to lower current flow through a circuit. The symbol for a resistor is a diagonally slashed line that is connected on each end of the slashes. Variable resistors, or resistors that vary resistance in response to a change in conditions, are shown as the symbol for a resistor inside a rectangular box. A diagonal arrow through the resistor indicates that resistance increases from low to high through the resistor. Potentiometers measure the change in voltage based on the position of a sensing needle on a variable resistance scale. The symbol for a potentiometer is that of a variable resistor with a vertical line from the lower center of the box to the center of the resistor. Thermistors are variable resistors that change their resistance in response to temperature. Thermistors can either be positive coefficient, meaning they increase in resistance as temperature increases, or they can be negative coefficient, meaning they decrease in resistance as temperature increases. A thermistor is shown in the wiring diagrams as the symbol for a resistor enclosed in an oval. Capacitors are used to store electric charge like a small battery, but they discharge quickly when power is removed. They're used in circuits to filter noise and prevent voltage spikes. Capacitors are usually part of a larger component and not shown in wiring diagrams. Switches are used to turn a circuit or load on or off. A switch allows current to flow through a circuit when it is closed and does not allow current to flow through the circuit when it is open. The symbols for switches vary depending on the type of switch. A normally open switch that is usually off is shown as an open gate, or as a rectangular bar over 2 circles. On a normally open switch, the bar and circles are shown as outlines only. A normally closed switch, one that is usually on, is shown as a closed gate between two dark gatepost circles, or as a heavy black bar that is across the tops of two black circles. A relay is an electromagnetic switch that is used to control high current circuits. The symbol for a relay is a box, with the electromagnet shown as a coil of wire. A normally open relay has the symbol for a normally open switch next to the symbol of a coil. A normally closed relay has the symbol for a normally closed switch next to the symbol for the coil. A transistor is an electrical switch that allows the flow of current through a circuit in one direction as a control current is applied to the base of the transistor. The symbol for a transistor is a perpendicular line that has a line on one side representing the base and a V-shaped line pointed to the perpendicular on the other side. An arrow on one side of the V indicates the direction of current flow when the control current is applied to the base. The common symbols for the loads that use electrical power are the symbols for motors and light bulbs. A motor is shown in the wiring diagrams as the letter M inside a circle. On each side of the circle are two smaller boxes. Single filament light bulbs are shown as a coil of wire inside a circle, while dual filament bulbs have two coils of wire inside a circle. Other devices such as rear window defogger grids and similar dedicated devices are usually shown as square or rectangular boxes that are labeled. Wiring diagrams and schematics typically identify the wires in a circuit by color and size. A chart in the repair manual will help you decipher the colors of the wires. A typical color chart lists the colors as B for black, W for white, R for red, P for pink, PU for purple, L for blue, G for green, Y for yellow, and GY for gray. Other colors are often used as well. Because of the number of circuits in a car, the limited number of primary colors is added to by the use of stripes on the wires. Where stripes are used, the main color of the wire is shown first, followed by a slash and the color symbol for the stripe. As an example, a green wire with a purple stripe would be shown as G/PU. In addition to color, wires are identified by their diameter. Wire diameters are graded in gauges on some vehicles, or the diameter of the wire is shown in millimeters on other vehicles. The lower the gauge of a wire, the larger the diameter. The larger the diameter of the wire, the less resistance to current flow. For example, the wire to a fusible link may be a thicker diameter 8-gauge wire, while a lamp bulb would have a smaller diameter 14-gauge wire carrying current to the bulb. Connectors, as the name implies, connect loads in a circuit to the wires that supply power and ground. Connectors are usually numbered in a wiring harness. The number typically uses a letter to distinguish the harness or group of wires that the connector is located in, followed by the number for that specific connector. The typical harness designations are E for engine harness and M or B for main or body harness. If letters are not used to identify the harness connectors, manufacturers typically group harness connectors in number series. For example, engine harness connectors are numbered from 100 to 199. Body connectors are numbered from 200 to 299, and so on. The terminals of the connectors are often numbered, either on the connector or in the repair manual. Wiring diagrams often differ on how a connector is displayed, but one common way to show terminals is by identifying the harness side of the connector separately from the terminal or load side of the connector. Most repair manuals show the locations of the connectors and the harnesses to make locating the connectors easier. Wiring harnesses are connected together by the use of junction blocks. Large junction blocks are often referred to as SMJs, or super multiple junctions. Junction blocks use male and female terminals to connect the wires of the different harnesses and are often bolted together. The terminals in the junction blocks are numbered for identification, either on the block itself or in the repair manual. Most repair manuals show the two halves of a junction block side by side. To determine which terminals align, you have to look at the layout as two facing pages of an open book. The terminals on the outer left and right edges go together, as do the terminals on the inner left and right sides of the pages. Splices differ from connectors and junction blocks in that they join wires with a soldered joint. Splices are often used to join several wires to a common ground. Splices are usually, though not always, insulated with heat shrink tube wrapping. Splices, where shown in wiring diagrams, are usually shown as a connector is with the letter S before a number indicating that it is a splice and not a connector. All circuits need a ground to complete the circuit. In wiring diagrams, the ground is shown as an inverted letter T with two or more smaller lines under the bottom forming a loose triangle shape. As with connectors, many repair manuals have a page dedicated to showing the location of the grounds in the engine and body harnesses. In order for an electrical circuit to do work, there needs to be a source of voltage, a load, and a ground. In addition to the basic components of a circuit, a protection device such as a fuse or circuit breaker is required to prevent damage to the wiring in the event that there is excessive current flow. Most circuits will also have a switch that controls the flow of current through the circuit. The wires in a circuit are routed through wiring harnesses that include junction blocks and splices. The loads are placed in the circuits with connectors that make both testing the circuits and replacing the components easier. Other devices such as resistors and diodes control the flow of current through a circuit. Before you begin troubleshooting any electrical problem, you need to know the circuit design, the function of circuit you're dealing with, and how the circuit is controlled. Let's take a look at the most common automotive circuits and components. A series circuit has only one path for current flow, and a break anywhere in the circuit stops current flow. A good example of a series circuit is the horn circuit. Parallel circuits are the most common automotive circuits. In parallel circuits, there are two or more paths for current to flow. This type of circuit has a great advantage. If a break occurs in one branch of the circuit, the remaining branches will still work. Series parallel circuits are just like they sound. The characteristics of both are combined. In this circuit, each bulb has its own power and ground point, but both bulbs are controlled by a switch and a rheostat located in the series portion of the circuit. Another important thing to keep in mind when identifying circuits is the location of the switch. If the switch is located between the battery and the load, the circuit is called load to ground because the load is hooked directly to ground. When the switch is open, voltage will only be present up to the switch. If the switch is located between the load and ground, the circuit is called switch to ground. If the switch is open, voltage is present through the load up to the switch. The most common tool that is used to test electrical circuits is a digital multimeter. The digital multimeter combines the functions of a voltmeter, ohm meter, and ammeter into one high-impedance meter that does not damage sensitive electronic circuits. If you notice, the functions of the digital multimeter tie directly to the three component parts of Ohm's law. Ohm's law, as we saw in the first video, expresses the relationship of voltage, current, and resistance in an electrical circuit. To review, Ohm's law states that 1 volt is required to move 1 amp through 1 ohm of resistance. Understanding the relationships expressed by Ohm's law is essential to troubleshooting electrical systems. The digital multimeter is your way to get the values of the voltage, amperes, and ohms in a circuit. These measurements will allow you to determine if the circuit is operating outside specification. If the circuit is operating outside of specification, we'll need to diagnose why the values for either voltage, resistance, or current have changed from the original specifications. The voltmeter function of the digital multimeter can be selected by rotating the selector knob to the V on the dial. Some multimeters will have a second option for testing voltage, that of a test in millivolts or thousandths of a volt. That can be used to check voltage in low-voltage electronic circuits. For most automotive tests, select the V function of the multimeter. Some digital multimeters will require that you either select a range for the data display or some auto-select the range for you. On manual range meters, the range that is selected determines the highest value that the meter will display. If a voltage over the manual set range is measured, the meter will read OL for over limit. To read that voltage, you will need to change the range of the meter. Auto range meters will automatically select the range of the meter to accommodate the measured values. With the meter set to the range of expected values, you can test for voltage in a circuit using the leads. The lead for the red probe is connected to the meter terminal marked V ohm, which is the terminal for voltage and resistance tests. The lead for the black probe is connected to the meter terminal marked COM for common. Voltage is the difference in the electrical charge between 2 points. Measuring voltage allows you to answer the following questions. Is voltage present? The presence of voltage tells you that the circuit is delivering voltage from the source to the point you are testing. What is the voltage level? The voltage level tells you whether the proper voltage is arriving at the point of the circuit that you are testing. And what is the voltage drop? The voltage drop tells you how much of the voltage is being consumed by the component. In order to do a voltage drop test, current must be flowing through the circuit. In other words, the circuit must be live. As we saw earlier, to do a voltage drop test, you test the circuit with the red probe at the point nearest the voltage source and the black probe on the point nearest the ground. The display will show the amount that the voltage drops across the load. Resistance in a circuit is measured in ohms using the ohm meter function of the digital multimeter. On the Fluke 88 digital multimeter, you can select the ohm meter function by turning the rotary selector to the ohm symbol. The leads of the ohm meter are connected to the same ports on the meter as are used for the voltage tests. The critical difference in using an ohm meter is that there must never be voltage present or current flowing in the circuit when you are using an ohm meter. The use of an ohm meter on a live circuit will damage the meter. The use of an ohm meter will allow you to answer the questions, is there continuity in the circuit? Continuity means that there is a path for the current to flow. A lack of continuity means that the circuit is open at some point and current cannot flow. Is the resistance of the component too high or too low? Resistance in the component affects current flow through the circuit. High resistance causes low current flow. Low resistance causes high current flow that can cause a fuse to blow. Setting the range of ohms is critical to understanding the readings on the display. The range of values on the Fluke 88 that can be selected manually are 400 ohms, 4 kilo ohms, 40 kilo ohms, 400 kilo ohms, 4 mega ohms, and 40 mega ohms. Each of the manual ranges represents the highest value that can be measured in that range. If a resistance is measured that exceeds that range, the display will show OL or over limit. If you are using the auto range feature for automotive tests, the display will show either ohms for readings under 400 ohms or K ohms for readings between 400 ohms and 399 kilo ohms, 399,000 ohms. A test for continuity is done to isolate the cause of a circuit malfunction. To test for continuity, make sure the ignition key is in the off position and disconnect the connectors to isolate a segment of the circuit. Touch the end of one probe to one end of the circuit segment and the other probe to the other end of the segment. A reading of 0 ohms for a segment that is a single wire indicates continuity. If the segment includes a load or other resistance, the meter will show the resistance for the entire segment of the circuit being tested. If the reading on the meter is OL, that means that the resistance in the circuit is over the limit of the meter. In a continuity test, that means that there is an open in the circuit of infinite resistance that current cannot flow across. Similarly, shorts to ground, where a portion of the circuit is bypassing the load, can be detected with a continuity test. With the circuit unpowered and the segment connector disconnected, connect the black probe to a known good ground. Connect the red probe to the power side of the circuit. If the segment of the circuit is shorted to ground, the meter will show continuity. To test a component for resistance, disconnect the component connector and connect the meter leads to the power and ground side of the component. The meter will return the resistance value for the component that can be compared to the specifications to determine if the component has the proper resistance. The ammeter function of the digital multimeter is used to test for current flow. Current is measured in amps. Current is the flow of electrons through a conductor. Testing current will allow you to answer the questions, is there a current flow? For a circuit to work, it must be complete and current must be flowing through the circuit. Is the current flow too low? A low current flow is indicative of a high resistance in a circuit. Is current flowing when it shouldn't be? A circuit that is using voltage when it shouldn't be will cause a drain on the battery when all systems are off. To use an ammeter, insert the black probe into the port labeled COM for common. Set the red probe into the meter port labeled amps. Set the rotary dial to the ammeter function for direct current. To test for current flow, the ammeter must be used in series with the circuit so that the current flows through the meter. If the meter has an inductive current clamp, you do not need to open the circuit for testing. If the meter does not have an inductive current clamp, disconnect the circuit from the battery or remove the fuse. Then touch the meter to the side of the break closest to the power source and touch the black probe to the side nearest the ground. The current flow through that portion of the circuit will be displayed on the meter. An open circuit means the current flow path has been broken. Some examples of an open circuit are a burned out light bulb, a broken or cut wire, or disconnected battery cable. A short circuit is a condition where an unwanted path for current flow is created, either to the ground side or positive side of the circuit. In most cases, a blown fuse is caused by excessive current flow from a short to ground or low side before the load. A short circuit to the positive or high side of a circuit can cause a component to operate all the time, regardless of switch position. Short circuits are probably the most difficult electrical problem to troubleshoot, especially if they're intermittent. If the circuit is shorted, you won't be able to use the voltage drop method because current must be flowing for voltage to drop. In a short circuit, there's usually no current flow because the fuse is blown, creating an open circuit. In addition to open and shorted circuits, there are other common circuit faults such as a loss of power, improperly working components, or inoperative or improperly operating loads. As we've seen, excessive resistance will cause a reduced current flow through the circuit. Where the resistance is extreme, no current will flow. Excessive resistance will cause lamps to glow dimly or cause electric motors to turn slowly. Excessive resistance is usually due to corrosion on connectors or terminals in the connectors that are loose. In this video, we've looked at the components of an electrical circuit, how the circuit elements are shown in a wiring diagram, and how to use a digital multimeter to test for voltage, resistance, and current flow. Thanks for watching.